विद्यार्थियों, ਅੱਜ ਦੇ ਪਾਠ ਵਿੱਚ ਤੁਹਾਡਾ ਸਵਾਗਤ ਹੈ। ਅੱਜ ਦੇ ਇਸ ਪਾਠ ਵਿੱਚ ਅਸੀਂ ਗਰੁੱਪ 16 ਐਲੀਮੈਂਟਸ ਬਾਰੇ ਪੜ੍ਹਾਂਗੇ। ਕੀ ਤੁਸੀਂ ਜਾਣਦੇ ਹੋ ਕਿ ਕਿਹੜੇ ਐਲੀਮੈਂਟਸ ਇਸ ਗਰੁੱਪ ਵਿੱਚ ਆਉਂਦੇ ਨੇ? ਮੈਨੂੰ ਯਕੀਨ ਹੈ ਕਿ ਤੁਸੀਂ ਸਾਰੇ ਹੀ ਜਾਣਦੇ ਹੋ ਕਿ ਐਲੀਮੈਂਟਸ ਆਕਸੀਜਨ, ਸਲਫਰ, ਸੈਲੇਨੀਅਮ, ਟੈਲੂਰੀਅਮ, ਪੋਲੋਨੀਅਮ ਪੀਰੀਓਡਿਕ ਟੇਬਲ ਦੇ ਗਰੁੱਪ 16 ਦੇ ਮੈਂਬਰ ਹਨ। ਫਰਸਟ वो ਐਲੀਮੈਂਟਸ ਨੂੰ ਕਲੈਕਟਿਵਲੀ ਕੈਲਕੋਜਨਸ ਕਿਹਾ ਜਾਂਦਾ ਹੈ, ਜਿਸ ਦਾ ਮੀਨਿੰਗ ਹੈ ਓਰ ਫਾਰਮਿੰਗ ਐਲੀਮੈਂਟਸ। ਇਹ ਸਭ ਨਾਨ ਮੈਟਲਿਕ ਕੈਰੈਕਟਰ ਦੇ ਹਨ। ਤੁਸੀਂ ਜਾਣਦੇ ਹੋ ਕਿ ਗਰੁੱਪ ਵਿੱਚ ਮੈਟਲਿਕ ਕੈਰੈਕਟਰ ਆਕਸੀਜਨ ਤੋਂ ਪੋਲੋਨੀਅਮ ਡਾਊਨਵਰਡਸ ਇਨਕਰੀਜ਼ ਹੁੰਦਾ ਹੈ। ਇਸ ਫੈਮਿਲੀ ਦਾ ਲਾਸਟ ਐਲੀਮੈਂਟ ਪੋਲੋਨੀਅਮ ਮੈਟੈਲਿਕ ਕੈਰੈਕਟਰ ਦਾ ਹੈ ਅਤੇ ਇਹ ਰੇਡੀਓ ਐਕਟਿਵ ਐਲੀਮੈਂਟ ਹੁੰਦਾ ਹੈ ਵਿਦ ਅ ਵੈਰੀ ਸ਼ਾਰਟ ਲਾਈਫ ਪੀਰੀਅਡ। ਪੋਲੋਨੀਅਮ ਦਾ ਇਹ ਨਾਮ ਪੋਲੈਂਡ ਤੋਂ ਪਿਆ, ਜੋ ਕਿ ਇਸ ਨੂੰ ਡਿਸਕਵਰ ਕਰਨ ਵਾਲੀ ਮਾਰੀ ਕਿਊਰੀ ਦਾ ਹੋਮ ਕੰਟਰੀ ਸੀ। ਉਸਨੇ ਇਸ ਦੀ ਖੋਜ 1898 ਵਿੱਚ ਕੀਤੀ।
Upon completion of this topic, the learner will be able to describe occurrence of group 16 elements, explain general characteristics of group 16 elements, explain chemical properties and trends in chemical reactivity.
ਆਓ ਹੁਣ ਗਰੁੱਪ 16 ਐਲੀਮੈਂਟਸ ਦੇ ਅਕਰੈਂਸ ਬਾਰੇ ਵਿਚਾਰ ਕਰੀਏ। ਕੀ ਤੁਸੀਂ ਜਾਣਦੇ ਹੋ ਕਿ ਆਕਸੀਜਨ ਇਸ ਗਰੁੱਪ ਦੇ ਸਾਰੇ ਐਲੀਮੈਂਟਸ ਵਿੱਚੋਂ ਸਭ ਤੋਂ ਵੱਧ ਮਾਤਰਾ ਵਿੱਚ ਪਾਇਆ ਜਾਂਦਾ ਹੈ। It occurs in the free form as O2 and makes up 20.94% by volume of the atmosphere. Most of it has been produced by the photosynthesis, in which the green coloring matter of plants, chlorophyll, absorbs energy from the sun and converts carbon dioxide and water of the atmosphere into glucose and oxygen. Oxygen makes up 46.6% by weight of the Earth's crust and is the major constituent of silicate minerals. It also occurs as metal oxide, ores and deposits of oxosalts such as carbonates, sulfates, nitrates, borates, etc. As water, it comprises 89% by weight of the oceans. Oxygen occurs as ozone, an allotrope of oxygen in the upper atmosphere, and is of great importance.
Let us have a look at the abundance of these elements in Earth's crust by weight as shown on the screen. The table is divided into 3 parts. At the extreme left, we find the name of the element. In the middle is the abundance in Earth's crust in ppm, and at the extreme right is the relative abundance of the elements. Oxygen 4.55 into 10 raised to the power 5, 1. Sulfur 340, 16. Selenium 0.05, 68. Tellurium 0.001, 74. Polonium traces. Children, let us learn about the general characteristics of group 16 elements. Let us begin with the electronic configuration of the elements. The elements of this group have 6 electrons in the outermost shell and have the general electronic configuration as ns2np4. The electronic configurations of these elements are as shown on the screen. You can see that oxygen has the atomic number 8 and electronic configuration of helium 2s2, 2p4. Sulfur has atomic number of 16 and has the electronic configuration of neon 3s2, 3p4. Selenium has atomic number of 34 and has the electronic configuration argon 3d10, 4s2, 4p4. Tellurium has atomic number of 52 and electronic configuration of krypton 4d10, 5s2, 5p4. And lastly, polonium has the atomic number of 84 and electronic configuration of xenon 4f14, 5d10, 6s2, 6p4.
आओ हुन एटॉमिक एंड फिजिकल प्रॉपर्टीज ते विचार करिए। ग्रुप 16 ਦੇ ਐਲੀਮੈਂਟਸ ਦੇ ਇੰਪੋਰਟੈਂਟ ਫਿਜ਼ੀਕਲ ਪ੍ਰੋਪਰਟੀਜ਼ ਨੂੰ ਇੱਥੇ ਟੇਬਲ ਵਿੱਚ ਵਿਖਾਇਆ ਗਿਆ ਹੈ। Let us have a look at the general trends in characteristic properties. We will first have a look at the atomic and ionic radii. The atomic and ionic radii of the elements of this group are smaller than those of the corresponding elements of group 15. Atomic and ionic radii of elements of group 16, as expected, increase on going down the group. Do you know why does this happen? Let me explain it to you. The comparatively smaller atomic and ionic radii of group 16 elements as compared to group 15 elements are due to the increase in effective nuclear charge of group 16 elements. As a result, there is great attraction of the valence electrons by the nucleus and hence radii are less. The increase in the radii of group 16 elements down the group is due to the increase in the number of electron shells. आओ हुन ionization enthalpies बारे विचार करिए. The ionization enthalpies of elements oxygen family are less than those of nitrogen family. As we move down the group from oxygen to polonium, the ionization enthalpy decreases. Have a look at the figures on the screen. ਕੀ ਤੁਸੀਂ ਦੱਸ ਸਕਦੇ ਹੋ ਕਿ ਇਹ ਕਿਉਂ ਵਾਪਰਦਾ ਹੈ? ਆਓ ਮੈਂ ਤੁਹਾਨੂੰ ਦੱਸਦੀ ਹਾਂ. We expect that the ionization enthalpy of oxygen should be more than that of nitrogen because of decrease in size. However, oxygen has unexpectedly low ionization enthalpy than nitrogen. This is due to the reason that nitrogen has completely half-filled orbitals and the configuration is stable because half-filled and completely filled configurations have extra stability. Because the configuration of oxygen is less stable and therefore has less ionization enthalpy. आओ हुन स्क्रीन ऊपर इलेक्ट्रॉनिक कॉन्फ़िगरेशन ते एक नज़र मारिए. Nitrogen has a completely half-filled orbitals and stable electronic configuration. Let us again have a look at the electronic configuration of oxygen, which is less stable than nitrogen. However, it may be noted that the second ionization enthalpies of the members of group 16 are higher than those of group 15. This is because after the removal of first electron, the second electron has to be removed from a symmetrical half-filled configuration as shown on the screen, which is more stable. As we move down a group, there is increase in nuclear charge, but at the same time, the atomic size as well as the number of inner electrons which shield the valence electrons from the nucleus increase. The overall effect of increase in atomic size and the shielding effect is much more than effect of increase in nuclear charge. Consequently, the outermost electron is less and less tightly held by the nucleus as we move down the group and hence ionization energy decreases. आओ हुन melting and boiling points ਤੇ ਇੱਕ ਨਜ਼ਰ ਮਾਰੀਏ. ਜਿਵੇਂ ਹੀ ਅਸੀਂ ਗਰੁੱਪ ਵਿੱਚ ਨੀਚੇ ਵੱਲ ਜਾਂਦੇ ਹਾਂ ਤਾਂ ਐਟੋਮਿਕ ਨੰਬਰ ਵਿੱਚ ਵਾਧੇ ਦੇ ਨਾਲ ਹੀ melting and boiling points ਵੀ ਵੱਧਦਾ ਹੈ. ਕੀ ਤੁਸੀਂ ਦੱਸ ਸਕਦੇ ਹੋ ਕਿ ਇਹ ਕਿਉਂ ਵਾਪਰਦਾ ਹੈ? आओ मैं ਤੁਹਾਨੂੰ ਦੁਬਾਰਾ ਦੱਸਦੀ ਹਾਂ. When we move down the group, the molecular size increases. As a result, the magnitude of the van der Waals forces also increases with the increase in atomic number and therefore melting point also increases. The melting point of polonium is, however, small. We will now discuss about electronegativity. The elements of group 16 have higher values of electronegativity than the corresponding elements of group 15. Oxygen is the second most electronegative element, the first being fluorine. The electronegativity decreases on going down the group. The decrease in electronegativity down the group is due to the increase in size of the atoms. ਹੁਣ ਅੱਗੇ ਅਸੀਂ metallic and non-metallic character ਬਾਰੇ ਵਿਚਾਰ ਕਰਾਂਗੇ। ਪਹਿਲੇ ਚਾਰ elements, namely oxygen, sulfur, selenium and tellurium, are non-metals. The non-metallic character is stronger in oxygen and sulfur and weaker in selenium and tellurium. On the other hand, last element is markedly metallic. However, it is radioactive and is only short-lived. आओ ਹੁਣ electron gain enthalpy बारे विचार करिए। The elements of this family have high negative electron gain enthalpies. The values decrease down the group from sulfur to polonium. Oxygen unexpectedly has low negative electron gain enthalpy. This is attributed to the small size of oxygen atom so that its electron cloud is distributed over a small region of space and therefore it repels the incoming electron. Thus, the electron gain enthalpy of oxygen is unexpectedly less negative in the family. We will next discuss the property of catenation. Catenation is the tendency of an atom to form bonds with identical atoms. In this group, only sulfur has a strong tendency for catenation. Oxygen also shows this tendency to a limited extent. Thus, the polyoxides and polysulfides of the types are shown on the screen. ਹੁਣ ਅਸੀਂ elemental state ਬਾਰੇ ਵਿਚਾਰ ਕਰਦੇ ਹਾਂ। Oxygen exists as diatomic molecule. Under normal conditions, oxygen exists as a gas. In oxygen molecule, there is a p-pi overlap between two oxygen atoms forming double bond. The intermolecular forces in oxygen are weak van der Waals forces and therefore oxygen exists as a gas. On the other hand, the other elements of family do not form stable p-pi bonds and do not exist as M2 molecules. On the other hand, the other atoms are linked by single bond and form polyatomic complex molecules. For example, sulfur and selenium molecules have 8 atoms per molecule and have puckered ring structure. The puckered ring structure of sulfur is shown on the screen. आओ ਹੁਣ allotropy बारे विचार करिए। All the elements of group 16 exhibit allotropy. For example, oxygen exists as O2 and O3. Sulfur exists in a number of allotropic forms of which yellow orthorhombic, alpha and beta monoclinic forms are most important. Selenium exists in 8 allotropic forms of which 3 are red monoclinic forms containing Se8 rings. The thermodynamically stable form is grey hexagonal metallic selenium, which consists of polymeric helical chains. The elements exist as common amorphous black selenium. The grey selenium is the only allotrope of selenium which conducts electricity. Tellurium has only one crystalline form having chain structure similar to that of grey selenium. आओ हुन oxidation states बारे जानिए. All the elements of this group have NS2-NP4 configuration in their outermost shell. Therefore, the atoms of these elements try to gain or share 2 electrons to achieve noble gas configuration. Therefore, these elements show 2 types of oxidation states. First, negative oxidation states. Oxygen has a very high value of electronegativity. It tends to achieve noble gas configuration preferably by gaining electrons. Thus, oxygen exhibits oxidation state -2 in its compound. However, there are a few exceptions in which the oxidation state of oxygen is not -2. For example, the oxidation state of oxygen in OF2 is +2, while in H2O2 it is -1 and 0 in O2 and O3. Since the electronegativities of these elements decrease as we move down the group, the tendency of these elements to show -2 oxidation state decreases down the group from sulfur to polonium. The least electronegative element, polonium, hardly shows -2 oxidation state. Secondly, we will discuss about the positive oxidation states. Oxygen does not show positive oxidation states except in OF2.
Unlike oxygen, the other elements also show oxidation state of +2, +4 and +6 due to the promotion of electrons to vacant d orbitals. For example, in the ground state, sulfur has only 2 unpaired electrons and can form 2 bonds. This accounts for +2 oxidation state of sulfur. If one of the electrons of p orbital is promoted to d orbital, there are 4 unpaired electrons available for bonding. Therefore, sulfur can show +4 oxidation state. On further excitation, one of the 3s electron is promoted to vacant d orbital and this makes available 6 unpaired electrons. This accounts for oxidation state of +6. Have a look at these on the screen.
Compounds of sulfur, selenium and tellurium with oxygen are typically tetravalent, that is, +4 oxidation state. Compounds of sulfur, selenium and tellurium show both oxidizing and reducing properties. Fluorine brings about the maximum oxidation state of +6 in its compounds. Compounds in +6 oxidation state show only oxidizing properties. The higher oxidation state becomes less stable when we move down the group. These compounds are covalent and hence are typically volatile. Chemical properties, trends in chemical reactivity. Let us discuss some chemical trends in the reactivity of elements. First property which we will discuss is reactivity with hydrogen. We will now learn about the formation of hydrides. All the elements of group 16 form hydrides of the type H2E, where E is equal to oxygen, sulfur, selenium, tellurium, polonium. For example, hydrides formed are H2O, H2S, H2Se, H2Te and H2PO. The hydrides of sulfur, selenium and tellurium are prepared by the action of acids on metal sulfides, selenides and tellurides respectively. H2S is prepared in the laboratory with Gibbs apparatus by the action of dilute sulfuric acid and ferrous sulfide. Let us have a look at the equation on the screen. Water is a colorless, odorless liquid, while hydrides of the other element of this group are colorless, bad-smelling, poisonous gases. Let us now have a look at the structure of these hydrides. All these hydrides have angular structure which involves sp3 hybridization of the central atom. For example, the structure of water is shown on screen, in which there are 2 bond pairs and 2 lone pairs. Due to the presence of lone pairs, the bond angle in H2O is less than the normal tetrahedral angle. It has been found to be 104.5 degree. As we go down the group, the bond angle in the hydrides decreases as shown on the screen. ਕੀ ਤੁਸੀਂ ਦੱਸ ਸਕਦੇ ਹੋ ਕਿ ਇਹ ਕਿਉਂ ਵਾਪਰਦਾ ਹੈ? ਆਓ ਮੈਂ ਤੁਹਾਨੂੰ ਦੱਸਦੀ ਹਾਂ। As we move down the group from oxygen to tellurium, the size of the central atom goes on increasing and its electronegativity goes on decreasing. Consequently, the position of bond pairs of electrons shifts more and more away from the central atom in moving from water to H2TE. For example, the bond pair in OH single bond is closer to oxygen than the bond pair in SH single bond. As a result, the force of repulsion between the bonded pairs of electrons in water is more than in hydrogen sulfide. In general, the force of repulsion between the bonded pairs of electrons decreases as we move from water to H2TE, and therefore the bond angle decreases in the same order as shown on the screen. This means that bond angle decreases from H2O to H2TE. Let us now discuss about the volatility. All the hydrides are volatile. The volatility increases from water to hydrogen sulfides and then decreases. This is clear from their boiling points as shown on the screen. Let us again have a look at the trend of volatility on the screen. आओ मैं ਹੁਣ ਤੁਹਾਨੂੰ ਉਹ ਕਾਰਨ ਦੱਸਦੀ ਹਾਂ ਜਿਨ੍ਹਾਂ ਕਰਕੇ ਇਹ ਵਾਪਰਦਾ ਹੈ। The high boiling point and therefore low volatility of water is due to the association of water molecules through hydrogen bonding. However, hydrogen bonding is not present in other hydrides. The intermolecular forces between the hydrides except water are van der Waals forces. These forces increase with increase in molecular size and therefore boiling points increase on moving from H2S to H2SE. ਹੁਣ ਅਸੀਂ acidic character ਬਾਰੇ ਵਿਚਾਰ ਕਰਦੇ ਹਾਂ। The hydrides of this group are weakly acidic in character. For example, H2S behaves as weak diprotic acid ionizing as shown on the screen. H2S ionizes as H positive and HS negative. HS negative ionizes to form H positive and S2 negative. The acidic character increases from H2O to H2TE as shown on the screen. Let me again explain you why does this happen. The decreasing acidic strength of the hydride is evident from their dissociation constant values shown on the screen. The increase in acidic character from H2S to H2TE can be explained on the basis of size of the central atom. As the size of the central atom increases in the order as shown on the screen, oxygen is smaller than sulfur, which is smaller than selenium, which is smaller than tellurium. The distance between the central atom and hydrogen also increases. As a result of increase in bond length, the bond dissociation enthalpy decreases and bond cleavage becomes more and more easy. Therefore, the acidic strength of the hydrides increases down the group. Let us now discuss about the thermal stability. The thermal stability of the hydrides decreases from H2O to H2TE as shown on the screen. Let me explain the reason behind this. On going down the group, the size of the central atom increases and therefore its tendency to form stable covalent bond with hydrogen decreases. As a result, the MH bond strength decreases and therefore thermal stability decreases. आओ ਹੁਣ ਅਸੀਂ reducing character ਬਾਰੇ ਵਿਚਾਰ ਕਰੀਏ। All the hydrides except water are reducing agents. The reducing power of these hydrides increases from H2O to H2TE as shown on the screen. This is due to the decrease in thermal stability of the hydrides. Greater the unstability of hydride, the greater is its reducing character. आओ ਹੁਣ ਅਸੀਂ other hydrides बारे विचार करिए. Oxygen and to a greater extent sulfur differ from the remaining elements in their tendency to form polyoxides and polysulfides, which are less stable than normal salts. The two common examples are hydrogen peroxide, which is fairly stable, whereas H2S2 is unstable and decomposes readily to give sulfur and hydrogen sulfide. The decomposition is accelerated by the presence of hydroxyl ions. H2O2 is a strong oxidizing agent, but H2S2 is not. H2O2 forms highly associated molecule because of hydrogen bonding, while H2S2 forms discrete molecules. Both H2O2 and H2S2 have similar skew structure. Sulfur forms a few hydrogen polysulfides called sulfanes. Some of these are shown on the screen. Formula is H2S2. Compound is hydrogen disulfide, and it is represented as H single bond, S single bond, S single bond, H. Formula is H2S3. Compound is hydrogen trisulfide, and it is represented as H single bond, S single bond, S single bond, S single bond, H. Formula is H2S5. Compound is hydrogen pentasulfide, and it is represented as H, S, 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 H, as shown on the screen.
आओ ਹੁਣ ਅਸੀਂ reactivity with oxygen, that is formation of oxides ਬਾਰੇ ਵਿਚਾਰ ਕਰੀਏ. All the elements of group 16 form two main oxides, EO2 and EO3, where E is equal to S, Se, Te or Po. In addition, they form other oxides as shown on the screen. Oxides of group 16 elements: oxide, sulfur, selenium, tellurium, polonium. Monooxides: SO, TeO, POO. Dioxides: SO2, SeO2, TeO2, POO2. Trioxides: SO3, SeO3, TeO3. Heptoxides: S2O7. Other oxides: S2O, S2O3, SO4. Oxides of sulfur are more stable than the corresponding oxides of other elements. For example, SO2 and SO3 are more stable than the corresponding dioxides and trioxides.
आओ पहला असी मोनोऑक्साइड्स बारे विचार करिए. All elements except selenium form monooxides. Sulfur monoxide is formed by heating a mixture of sulfur dioxide and sulfur under reduced pressure at 425 to 475 Kelvin. It can also be prepared by the action of silver on thionyl chloride as shown on the screen. आओ हुण दूजे पॉइंट डाइऑक्साइड बारे विचार करिए. All the members of oxygen family, sulfur, selenium, tellurium and polonium, form dioxides of the formula EO2. For example, sulfur dioxide, selenium dioxide, tellurium dioxide and polonium dioxide. The dioxides are obtained by direct union of elements as shown on the screen. The dioxides of these elements differ considerably in their properties and structure. Sulfur dioxide is a gas at room temperature.
In SO2, sulfur atom undergoes sp2 hybridization. Two of the three sp2 hybrid orbitals form sigma bond with 2 p orbitals of each oxygen atom. The third sp2 hybrid orbital is occupied by a lone pair of electrons. Thus, SO2 has bent or angular structure. Two unhybridized pz and d orbitals of sulfur atom form p pi bond or p pi d pi bond with pz orbital of each oxygen atom. Since one of the orbital is occupied by a lone pair of electrons and the repulsion between lone pair bond pair is more than between bond pair, the bond angle of OSO is slightly reduced from 120 degree to 119.5 degree. As is clear, the 2 pi bonds are different because one is formed by p pi overlap and the other is formed by p pi d pi overlap. But actually both the SO bonds have exactly same bond length, that is 143 picometer. This is because of resonance between two structures. The SO2 molecule is resonance hybrid of two structures. The multiple bonding in SO bond in SO2 is due to p pi or p pi d pi bonding. In addition, it has been suggested that there is possibility of p pi d pi bonding due to overlap of filled p pi orbitals of oxygen with vacant 3 d orbitals of sulfur as shown on the screen. Like sulfur, other elements also form dioxides. SeO2 is a white crystalline solid. In the gaseous state, it exists as discrete molecules having structure similar to SO2. In the solid state, it has a polymeric structure consisting of infinite chains. Tellurium oxide and polonium oxide are also non-volatile crystalline ionic solids and each occurs in two crystalline forms.
आओ हुन trioxides बारे विचार करिए. All the elements of this group form trioxides of the formula EO3. Amongst trioxides, sulfur trioxide is most important, while selenium trioxide and tellurium trioxide are also known. Sulfur trioxide is prepared by direct combination of sulfur dioxide and oxygen in the presence of finely divided platinum of divanadium pentoxide at 2 atmospheric pressure and 450 degrees centigrade. The vapors of sulfur trioxide formed are collected in a receiver and cooled by freezing mixture. It can also be prepared by the dehydration of sulfuric acid with phosphorus pentoxide. Sulfur trioxide can also be prepared by heating ferric sulfate, which decomposes to give sulfur trioxide.
Sulfur trioxide has trigonal planar structure in the gaseous state in which sulfur atom is sp2 hybridized. The 3 sp2 hybrid orbitals of sulfur overlap with p orbitals of oxygen to form 3 SO sigma bonds. The sulfur atom in the excited state is now left with 1 p and 2 d orbitals which overlap with p orbitals of oxygen to form 3 pi bonds. In the 1p orbital of oxygen form p pi bond with p orbital of sulfur, while with 2 oxygen atoms overlap with d orbitals of sulfur atom forming p pi d pi bonds as shown on the screen. Therefore, SO3 molecule has a trigonal planar structure. The bond angles in SO3 are exactly 120 degree each and SOO bond lengths are 142 picometer. Although the 3 SO pi bonds are different, that is 1 p pi and 2 p pi d pi, yet they are equal because of resonance as shown on the screen. The molecules of SO3 are held together by weak van der Waals forces of attraction. Therefore, it exists as a gas at room temperature. However, in the solid state, it exists as linear polymeric chain structure or cyclic trimer as shown on the screen. Selenium trioxide is prepared by the direct oxidation of selenium or selenium dioxide. It is a white hygroscopic solid having melting point 118 degrees Celsius. It exists as monomer in the vapor state A and as a cyclic tetramer Se4O12 in the crystalline state.
ਹੁਣ ਜਦੋਂ ਕਿ ਅਸੀਂ ਇਸ ਪਾਠ ਰਾਹੀਂ ਕਾਫੀ ਕੁਝ ਜਾਣ ਚੁੱਕੇ ਹਾਂ ਤਾਂ ਕੁਝ ਸਵਾਲ ਪੁੱਛ ਕੇ ਇਹ ਪਤਾ ਕਰਦੇ ਹਾਂ ਕਿ ਤੁਸੀਂ ਅੱਜ ਦੇ ਇਸ ਪਾਠ ਵਿੱਚੋਂ ਕੀ ਕੁਝ ਸਿੱਖਿਆ ਹੈ. My first question is, why bleaching by sulfur dioxide is not permanent? And here's the answer. The bleaching by sulfur dioxide is not permanent. The reaction is an unstable and reversible one. When exposed to the atmosphere, the bleached matter gets oxidized and regains its original color. Bleached matter plus oxygen gives original color. Dipping the bleached article in dilute sulfuric acid can also restore the original colors. ਬੱਚੋਂ, ਮੈਨੂੰ ਉਮੀਦ ਹੈ ਕਿ ਤੁਹਾਨੂੰ ਅੱਜ ਦਾ ਇਹ ਪਾਠ ਕਾਫੀ ਦਿਲਚਸਪ ਲੱਗਿਆ ਹੋਵੇਗਾ. ਧਿਆਨ ਦੇਣ ਲਈ ਸ਼ੁਕਰੀਆ. ਅਗਲੀ ਵਾਰੀ ਇੱਕ ਹੋਰ ਨਵਾਂ ਵਿਸ਼ੇ ਦੇ ਨਾਲ ਫਿਰ ਮਿਲਾਂਗੇ. ਤਦ ਤੱਕ ਲਈ ਇਜਾਜ਼ਤ.